Before we move on to the constitutive equation, I wanted to give one example of the use of integral equations of conservation. And this is example 4.4 in Kundu. And the idea here is to look at a bar, like a metal bar, long metal bar, and I'm drawing the cross section here. So this bar goes into the page and it is long and straight and has this cross section with a characteristic dimension d. And it's in a flow field, it's placed in a flow, and the question is, how much drag force does the flow impose on the bar? Or put differently, what force do we have to put on the bar to keep it in place and not move with the flow? So the drag force would be my Fd, and the sign convention is that positive drag force on the bar is in the direction that the bar would accelerate. So if we think of the drag force pushing against, like the bar onto the fluid, it's minus Fd here. So at a far distance upstream of the flow, we have a uniform flow coming in. This is the background flow, U infinity, at pressure P infinity. And then downstream, the flow field will have changed. The drag force that is exerted onto the bar means that our flow field has been decelerated. So now our flow field will look something like this. U as a function of y, where my coordinates are x and y, chosen like that. So the question is, what is the drag force required to hold the bar in place? So what is minus Fd? And really we're interested the drag force per unit length. So L here is length into the page. So what is Fd over L? i.e. the drag force required to hold bar in place. Let me move this down a bit. Okay, the way we go about this is we first pick a control volume, and then we apply the conservation of mass and momentum over this control volume. So the control volume has some height h, and h, so this is h. H has to be large enough that at the top and bottom boundaries you don't have shear stresses anymore. And also at the top and bottom boundaries, so this is top, bottom, the horizontal components of our flow is approximately U infinity. There is a non-zero vertical component, and that is because the streamline around our bar will look something like this. So there will be flow out through the top and bottom surfaces. And near the outlet here, okay, so this is the inlet, and this is the outlet. And near the outlet, we have nearly horizontal streamlines again. Same at the inlet, we assume that this distance here between the inlet and the bar allows that there's no effect of bar on the upstream flow at the inlet. So the red box here is our control volume. And just for completeness, I'm going to say consider a long bar in 2D flow. So it's 2D, meaning that our vector u, vector field, velocity field u is a function of u and v. So let's write our mass conservation equation. Number one, mass conservation is d by dt integral, and here we're using the integral formulations, right? So integral over the control volume v star plus the integral over the control volume's surface area rho u minus b dot n dA equals 0. So this is mass conservation, and we can simplify this quite substantially since this is a steady flow field and we have a control volume at rest. So that means steady flow d by dt is 0. So this whole term is 0. And the control volume is also at rest, so b is 0. Control volume at rest. And this is 0 because steady flow. The second conservation equation is momentum. And here again we have the transient term plus the surface term a star rho u minus b dot n dA, and that has to equal the volume force term rho g dA plus the surface force term. And this is our momentum conservation over the control volume. And here again we can simplify this. Terms drop out. Same with the b again. And also we don't consider any body forces here. Yeah, so we're just looking at the drag forces due to the bar itself. And you can count the equations here, and this is really 4 equations, 1 from the mass conservation and 3 from the momentum equation. 1 equation, 3 equations, and we have 4 unknowns, so we can solve these simultaneously.